So the FAT file system is very simple, a little old, but still in use. For example, many USB drives still use FAT32. And the development of the FAT file system with MS-DOS. It was the standard file system of Windows 95, 98, NT. Yeah, but nowadays, as you probably already know, the standard file system of Windows is NTFS. Yeah, but it still makes sense to have a look at FAT. As I said, it's still in use for USB drives, for example. There's also exFAT, which is another version of FAT that is also mainly or was also mainly developed for USB drives, while the FAT file system itself was developed in according to MS-DOS and with MS-DOS. Okay. And the FAT file system has some special bytes, also the NTFS file system, and they were like introduced to both of these file systems in order to keep them apart. And if you plug in an NTFS formatted disk and a FAT formatted disk into your Windows computer, then the special bytes are getting checked, and you cannot have, for example, both special bytes. It was a mechanism to differentiate between those two standard Windows file systems. Maybe let's start with the development of FAT first before I go more into the details of the file system structures. Okay, so on this slide you can see a picture of the Microsoft Corporation in 1978, so a pretty old picture. Can anybody tell me, can you see some familiar faces on that picture? If you recognize anybody, type it in the chat. So during that time period, the FAT file system was created, as I said, along with MS-DOS. And you maybe you could recognize a familiar face. No one? Okay, so here, that person here is Bill Gates. Yeah, okay, one person, two persons. Okay, yeah, this is Bill Gates. And let me check that. So in the top row, you have Steve Wood, Bob Wallace, Jim Lane. Then you have Bob O'Rea, Bob Greenberg, Mark McDonald. So Mark McDonald and Bill Gates, they developed FAT together. Then you have Gordon Ledwin, Bill Gates, Andrea Lewis, Marla Wood, and Paul Allen. Yeah, so to be honest, I knew Bill Gates and that was it. Actually, Mark McDonald also played a major role in the development of FAT and a major role in the Microsoft Corporation. Okay, so now you get an impression on how old that file system is. This is also why FAT is one of the most well-examined file systems in general. It's one of the most simplest file systems. I mean, it's pretty obvious because back then, like computers themselves were very simple. Their drives were very small. Therefore, there was no need for like very complex file systems and very complex data structures. So this is why it's one of the most simplest and also one of the most or best understood file systems. It was primarily used in DOS and some older Windows versions, but it's still supported, as I said, and still in use. Yeah. And FAT is especially interesting from a digital forensics point of view, because it has many places where data can be hidden. Yeah. Yeah. And as I said, it's a good starting point if you want to learn more about file system structures in general and how they work, how they manage data. FAT uses a few very simple data structures, which is yeah. So modern file systems, they have more complex data structures, more data structures in general, but FAT has a couple, like very few simple data structures, and we will have a look at basically all of them. For example, with NTFS, we couldn't discuss every single data structure that NTFS supports, because we would need like a couple of hours for that. But with FAT, it's absolutely doable. One problem that we have is that FAT does not quite follow the scheme, or it does not fit into the 5 data category scheme from Brian Carrier. There are a couple of data structures that fit into several data categories, but still having these categories helps unifying or talking about different file systems, or comparing them, talking about them using a unified interface for tools, also unify the output of forensic tools, like the data categories, even though they do not fit in every single case, they are still helpful. Okay. So let's talk about some basic concepts. There are 3 major FAT versions. There's FAT 12, 16, and 32. I already told you that there's also exFAT, so extended FAT, which was primarily developed for SD cards, but also USB drives. We will not discuss that one in detail here, because it's more complex than these 3. And B, I just want to give you an introduction in some file systems, and you will see after we discuss the 3 bigger file systems that I plan to discuss with you, that if you understand like one file system, you are probably also able to understand other file systems with a little research and checking out the data structures. But they all have the same task. They all function very similar, but they differ in their data structures or the layout of their data structures. So we do not need to discuss every single one. So this is why we will not talk about exFAT, but we will talk about these 3 versions of FAT. They all follow a very similar layout. The difference is the size of certain data structures, which is indicated by the number. And each file and directory in a FAT file system has a directory entry. And what a directory entry is, we will see now. So here you can see example directory and a very simplified example directory of a FAT file system. So let's say we have a file, it's called file.dat. It has a certain size, and it has a starting cluster. So this is what the directory entry tells us: the name, the size, and the start. Each file and directory in FAT has one of these directory entries. And besides these free information fields, it also contains additional information, additional metadata. But as I said, let's stick to that simplified version for now. So what you can do with the directory entry is you can have a look at where the file starts first, for example. So let's say it starts in cluster 34. And this cluster then contains a reference to the next cluster. Or, okay, that was probably a little confusing. So the FAT, the file allocation table, contains, for every single cluster, it contains a reference to either the next cluster of a certain file or an end of file marker. So what you can do with the directory entry is you can have a look at the starting cluster, and then you have to have a look at the file allocation table and the entry for the starting cluster. And it tells you in this example that the next cluster of that file is cluster 35. So you can go into that cluster and check out the file allocation table entry for that cluster. And there you can see that it tells you end of file. And now you know that file.dat, two clusters belong to file.dat, namely cluster 34 and 35. And these directory entries, directory is the official name of this data structure, but Carrier, for example, and I think also the sleuthkit calls that inode. And this inode term is used mainly in the X file system, but because Brian Carrier wanted to have this unified output and that unified interface for his tool, he also called the directory entry of FAT, for example, an inode. The official name is directory entry. Okay. So I think I told you everything that you need to know about the directory entry and FAT allocation table for now. Let's have a look at the five categories according to Carrier. So the first one you should always have a look at is the file system data. Okay, there's a question in chat. I'll go back to that slide. What does the 4000 byte entry indicate? It seems the size is determined by the linked cluster list. That's correct. If you have the cluster list, you can also calculate the size of the, you can call, okay, that's not correct. Let me start from scratch. So when you have the cluster list, you know how many clusters are allocated for the file. But the file content itself could be smaller. So the 4000 bytes tell you how big the file really is. It could be less than 2 clusters, for example, then you would have slack space. So you could calculate the how do you say it, like the maximum size of the file, for example, only with the cluster linked list, but the actual size of the file is stated in this field here. Okay, let's talk about file system data. Okay, let's go back for 1 second. Can anybody tell me what file system data tells us? What is part of file system data? So we have 5 categories. We have file system data, we have content data, metadata, file name data, and application data. The first category you should check out is file system data and what can we gain from file system data. Maybe the locations of the tables. Yes, correct. What else? Type of file? Nope. It's file system data. Any ideas? The location of certain data structures is correct. The location of a file, nope. Starting sector of the file system would be correct. So as the name tells us, magic bytes to show what file system it is using. Yeah, so the name already tells us what file system data actually does. It tells us everything we need to know about the file system itself, about the layout of the file system, the location of important data structures, magic bytes, starting sectors, where to look at in order to process the file system. So file system data tells us in this case, for example, everything we need to know about the FAT layout. So where to find the boot sector, how big is the reserved area, how big is the FAT area, where does the data area start, where can I find the root directory. All these information is part of the file system data. So data about the file system. And here you can see, this is a general FAT layout, and here you can see that the FAT file system is designed to occupy the whole disk and also override, for example, the boot sector of a DOS MBR partition. And therefore we have an additional boot sector here. Or in general, like, yeah, it is not necessary to have an additional boot sector here. And I think it is also not done nowadays that you have a file system like FAT that overrides like the whole disk, and then you have no partitions anymore. But it's like a remainder of a data structure that is still there, but it's not used anymore, or the purpose was a different back then. So it was designed to override the whole disk and also override the boot sector. This is why the boot sector is still here, but this is not done anymore. Usually you have like your regular partition scheme. You have the boot sector in the beginning of your disk. You have your partition table, and then you have your partitions. And inside one of these partitions could be, for example, a FAT file system. And then you would have an additional boot sector, which doesn't need to be used. This is how it's done nowadays. Yeah, but just that you know, this is why the boot sector is still here. And FAT, separates the partition or the disk into 3 areas. We have the reserved area, the FAT area, and the data area. The reserved area is reserved for the boot sector. The FAT area contains the file allocation table, and the data area contains the root directory as well as the data itself. Yeah, and the reserved area is also oftentimes called the BIOS parameter block, or not often, sometimes called BIOS parameter block. But I just tell you that you heard about that in case you read the name somewhere, but you don't really have to know that this block also has like certain different other names. Okay, let me check my notes. Okay, the data area is the first area where we have differences according to the version of the FAT file system. So as you can see here, for FAT 12 and 16, the root directory, and we will talk about that data structure later. The root directory is one of the most important data structures, or the second most important data structure after the file allocation table. And for FAT 12 and 16, you can always find it at a fixed location at the beginning of the data area. But for FAT 32, it could be somewhere in the data area. So yeah, you have to check out the reserved area or the file system data in order to find the root directory for FAT32. Another difference is that FAT32 contains a backup copy of the file allocation table and a special data structure called fsinfo to quickly find unused file system blocks. But I think these are the only differences between these versions. Okay, here you can see what I just told you about again. So we have this one of the most important information in the file system categories is, as you already said in the chat, the location of certain files and areas. So what you need to know is that the start address of the reserved area is always sector 0 of the partition. And for FAT 12 and 16, the reserved area is one sector big in size. For FAT 32, we have the reserved area here. It doesn't necessarily need to be of size 1. It can also be bigger. And you also have a reference to the root directory in the reserved area in the case of FAT32, because as I said, the root directory can be somewhere in the data area, and therefore you need to have a reference to it in order to find it. So this information is included in the reserved area. For FAT 12 and 16, it's not included because the root directory is always at the beginning of the data area. Okay. Okay, so the FAT area contains one or more FATs. So in this case, you have one FAT in the FAT area, and FAT32 could have two FAT file allocation tables in the FAT area. If that's the case, this is also indicated in the reserved area. So the reserved area, all the file system information you need in order to find all the data structures and have all the information about the data structures that you need. So in case you have more than one FAT file allocation table, then you will find a certain flag in the reserved area. And And I think, yeah, because here you only have one FAT, the size of the FAT area is the size of that one FAT. And because here you can have two FATs, the size of the FAT area is the number of FATs times the size of the FAT. Okay, and what you need to know about file system Slack for FAT is that after the end of the last cluster, there could still be a few unused sectors. And data may also be hidden between the end of the last valid FAT entry and the start of the data area or the backup FAT. So here you can have some slack space in cases where the FAT isn't fully used. So the FAT has a certain size, but not all of the entries must be used. So before the data area starts, there could be unused space here where people could hide data. And yeah, in the data area, everything is organized in file system blocks or clusters. We already talked about what a cluster is. And yeah, so for the data area, we also have a difference in FAT12 and 16 and FAT32. So for FAT12 and 16, the start of the data area is the root directory. And for FAT32, the start of the data area is just the next sector after the FAT area, but we don't know what lies in the first sector. For example, there could be a file, there could be the root directory, there could be whatever. Okay, let me check my notes. Okay, there is a question in the chat. Why did they make the decision that the root directory in FAT32 can be anywhere? Is there a benefit? I don't see. Okay, I don't know for sure, but what I can think of is that because they made the decision that in the FAT area there can be two FATs, for example, with FAT32, maybe they wanted to design it in a way that the FAT area could grow and in order to make that possible, they decided not to put their root directory in the beginning of the data area because they then probably had to copy it somewhere. But actually, I don't know why they made that decision. I think it has something to do with the FAT area and the fact that we now can have more than one FAT. Yeah, but yeah, as I said, I don't know for sure. Okay, let me check the notes very quickly. Yeah, okay. What is also important is to know is that I told you that the number after the FAT name, so the version of the FAT file system gives you a hint about the size of a certain file system structure. And it actually tells you the number of bits you have in the file allocation table to address. So the size of the entries in the file allocation table. Okay, and therefore, the bigger the number or the bigger the version, you have a bigger maximum size of clusters in the file system. So in FAT12, you can address less clusters than in FAT16, and in FAT16, you can address less clusters than in FAT32. So this is what it tells you. Okay. Yeah, okay. Yeah, and the FAT file system is always the clusters of the cluster size of a FAT file system is always set to the maximum size, so it cannot grow dynamically. Um, and yeah, this is the maximum number of clusters, and the maximum cluster size is also the reason why you cannot, why FAT isn't very good in handling very large files. So this is actually the reason why Microsoft decided that they need to have another or a newer version of a file system, and therefore crafted NTFS. Okay, so let's talk about the boot sector very quickly. So essential data in the boot sector is the start address of the reserved area, which should be, as we said here, which should be like the first sector of the partition. Yeah, the size of the reserved area. Also, as I said, the number of FATs in the FAT area, the size of the FAT, the number of sectors per cluster, and the root directory, the root directory location in FAT32, but not in FAT12 and 16. And we also have non-essential data in the boot sector. For example, in the boot sector, you can find something that is called OEM name. Yeah, it's something where tools can put a string in to indicate what the file system is used for. Yeah, but as the name already says, it's non-essential, so you can basically put in there anything you like, and you can also change that. So you could, for example, hide a very small amount of data here. Yeah, so certain Windows applications or Windows versions put a string in that field, but yeah, they don't need to. Yeah. And yeah, as I said, anyone can easily change that string with a hex editor. So this string must not be correct. Can FAT32 have more than 2 FATs, or is 2 the limit? I think you can have several numbers of FAT, but I'm not quite sure. So usually you have 2, yeah, one original FAT and one backup FAT. So usually you don't have the need for more than 2 FATs. But I think it's possible. But I need to check that and have a look at the carrier again. I'm not quite sure. But I think because I put numbers of FATs on the slide, I think it's more than 2 are possible, but you will probably never see that. Even 2 are pretty rare. Yeah, okay. But I'll check that. Okay, so that being said about non-essential data in the boot sector, obviously that kind of data is the more important one, and the one you should absolutely check when you analyze a file system. But this data you should also check because somebody could write something in there. I mean, it's not much, but yeah. But you cannot trust what's in there. Okay, we have more non-essential boot sector data. You also have like a 4-byte serial number in the boot sector. It's a unique number, and it depends on the creation time and something else, which we don't know what it is. Yeah, but also here, like the number doesn't necessarily need to be correct. I mean, you could use it to check whether the file system is a removable medium and has been exchanged. Yeah, but as the data doesn't necessarily have to be correct, you should be careful when using that kind of data. The boot sector also contains a string which indicates what kind of file system it is. But that data also doesn't necessarily have to be correct. And we have a drive name. It's yeah, as the name suggests, it's a name for drive. You can put something in there. It doesn't really matter, but yeah. The number is also saved in the root directory, so you could check if these two drive names align. But I think you cannot really gain much from that. But just that you know, it also contains this drive name. Yeah, but it's non-essential data. Okay, and the boot sector obviously also contains boot code. This code is jumped to by the DOS MBR boot code. The first 3 bytes of the boot code contain another jump instruction, and yeah, it basically just jumps to the rest of the boot code after it did some configuration. And yeah, so we have different sizes for the boot code in the boot sector depending on the FAT version. So for FAT 12 and 16, we have 62 to 509 bytes in the boot sector, and for FAT 32, it's a little, yeah, the minimum boot size is a little bigger. And you can also have like further sectors behind the boot sector for more boot code. I think I told you last time that checking out the boot code can be necessary when there is a hint for boot sector viruses, for example. Yeah, other than that, you probably don't need to have a look at the boot sector. But yeah, if you think there might be a boot sector virus, then you should check out the DOS MBR boot code, but also the FAT boot code. Yeah. And FAT file systems also have a boot code, even though they are not marked as bootable. So they always have it. And I think I explained on a couple of slides before why that is. And you can use fstat to have a look at boot code if necessary. So when you want to analyze the boot sector, you should first check out the essential data, especially to determine the file system type. This is especially interesting or necessary because we now know that the root directory location depends on that and a couple of other things. You could check out if you can find hidden data there. Yeah, so if the boot code is normally, like the boot code is normally located in the beginning of the file system and doesn't necessarily need all of the space. So you could check out if there's something hidden in there. Or as I said, you could check out if there's some kind of boot virus in there. And yeah, so important to note is also that in FAT32, many sectors are reserved after the boot sector. I already told you about that, and there could be slack space. The reserved area is usually deleted during creation, but somebody could hide something on purpose in there. So you will probably not find old data in this slack space area, but you could find hidden data. Okay. I also already told you that FAT has a backup boot sector. Usually it can be found in sector 6, but it doesn't necessarily has to be in sector 6. And you can use the backup boot sector for sanity checking the original boot sector and to find manual manipulations or boot viruses where people maybe didn't know that there's also a backup boot sector. Okay. So now that we know about file system data, we should check out the content data. What is content data again? Can anybody explain it in the chat? What can I do with content data? The actual data contained in the file. Exactly. So the fundamentals of content data can be seen here. Best transition ever. So content data actually tells us something about the content of a file, for example. And in order to find the contents of a file, we need to check out the directory entries we talked about earlier and the file allocation table. And we also have data that describes the file itself or the directory. And the contents are organized in clusters. We already knew that. Clusters are consist of several sectors, and the clusters for the data content, they start with the address 2. The cluster 0 and 1 are not used for content data in FAT. So here you can see the layout or organization of content data in the data area for FAT 12 and 16. We have some unused space in the beginning. So the first sector of the data area contains the root directory, so it's not unused but not usable for content data. And then the first usable data cluster starts with address 2. And for FAT32, we have the first cluster of the data area that is addressable with sector address 2. And then in there somewhere we have the root directory. Okay. Yeah, and let me check out my notes. Yeah, and I mean, I think I already told you that, but I will repeat it. So the first cluster for files in the data area is not is not cluster 0 and also not cluster 1, but cluster 2. And it's important to know that the first cluster for the file allocation table also accordingly is not at the beginning of the file system and not cluster 0. So when you check out the file allocation table, don't ask yourself where cluster 0 and 1 is. Just to make that extra clear. Okay, and yeah. Let's check out how we calculate the sector number for a file system block. So we already talked about the fact that a cluster is made up of certain sectors. And let's say we have a logical drive address A of cluster 2, and we have the number of sectors per cluster, and a logical file system address C, and we want to have the logical drive address of cluster C. Then we can calculate that by using that formula. So we want to have like a certain address of a sector in the data area, and we have to keep in mind that the area before the data area can have a certain size and use a certain number of sectors. And in order to find cluster 2, we need to calculate that, or we need to know that first in order to calculate that number. It's a little confusing, but do you know, do you get what I'm trying to tell you? Like, you have to be careful and pay attention when you try to calculate the logical file system address of a certain sector or cluster in the data area, because you have that space A here that can be of the size X, and that need to be added to your actual number of sectors per clusters times the logical system address -2, because we have cluster 2. Do you get what I'm trying to say, or is it too confusing? I just want to tell you that you have to pay attention when calculating addresses in the data area. Maybe we'll go ahead, and if there is any questions later, we can talk about it again. Okay, so we're still in the content data category. So in that category, obviously we also want to be able to check the status of a certain cluster in the data area. Since we want to know if data is stored in a certain cluster. And I already told you that the file allocation table has one entry per cluster in the data area, which gives us the allocation status of each cluster. And the size of the entry depends on the FAT type. So when you check out the file allocation table, there could be, or you could observe several values that have several meanings. For example, if you find out that for a certain cluster you have the value 0 in the file allocation table, then this means that this cluster is currently unallocated and doesn't belong to any file. If you observe one of these values and the length of the value depends on the FAT type, then it tells you end of file. So this is the end of a file. So that cluster belongs to a file and it's the end of the file. If you observe one of these values, it means that the cluster is damaged. And all other values means that the cluster is currently allocated to a certain file. Yeah, and the order in which the clusters are allocated to certain files depends on the operating system and also the file system driver, which is dependent on the operating system. Okay, and the good thing with FAT is that if a cluster is set to the unallocated status, so for example, we have a file in cluster 34. It contains some kind of value because the cluster is occupied, then we delete the file, then the cluster is set to 0 in the file allocation table, but the content of the cluster is not deleted. So we only the status of the cluster is changed, but the cluster itself is not deleted. And that's pretty good for digital forensics. So if you want to analyze content data, you should first search for all unoccupied clusters. You can do that by going through the file allocation table. And then you could check out the content of that clusters. You should also check out clusters that are marked as damaged because we talked about it a couple of times by now. So this could be done manually in order to hide data. And you can also use, for example, ScanDisk or Format. Programs like ScanDisk or Format, they often leave sectors marked in this way untouched. So you should not use these programs in order to analyze them, but you could check them out manually by yourself. And obviously, you should also check out SlackSpace. Okay. Okay, so next data category we have to talk about is metadata. What does metadata tell us? What can we gain by analyzing metadata? Somebody? Dates, file sizes, extensions, credits, versions. Okay, good. Additional, possibly no needed info on the data, maybe last modified, etc. Okay. Yeah, so one of the most important things in digital forensics is timestamps, and timestamps, for example, would be metadata. Yeah, but all your suggestions were pretty good. So let's have a look at metadata. We already discussed that there is a directory entry for each file and directory. It's usually 32 byte in length. And so in FAT, in the FAT file system, metadata is relatively closely linked to the file name data category. So this is where it becomes a little mixed. So metadata in FAT file system also contains file names, a couple of attributes that tells us something about the file size, and the logical file system address of the first cluster. And obviously also access times, so timestamps, which is very important for digital forensics. And because the metadata for files and directories also contain the file names, this is why it's like some kind of hybrid category or hybrid data belong to the file name and the metadata category. So here you can see the structure of a directory entry. In the first byte, we have the first character of the object name and allocation status of the object. We will come to that later. Then we have the other 2 to 11 characters of the object name. Both of them are essential data. We have the attributes that I already mentioned. We have some kind of reserved space. We have the time of the object creation in tenths of seconds. We also have additional timestamps in hours, minutes, and seconds. Yes, there's something else that is important. Another timestamp here, another timestamp here, and of course the size of the object in byte. And so the first 11 bytes are very important. The first 11 bytes of the directory entry of a file or a directory, because it not only gives us the name of an object, it also tells us if the object was deleted or not. So the first byte tells us if an object is still active or if it was deleted. So for example, we have a file that is called, let's say, file. Then we have an F in the first byte. And then we have IL here in the following bytes. And if that file is deleted, the F is removed and only IL remains. But that's it. Like, yeah, this is the indicator for a file that is deleted. So what you can do with that is you can restore most of the file's name, even though it's deleted. And that's pretty good for digital forensics. Yeah, and the reason why we have the limitation to 11 characters for the file name is because there is a DOS naming scheme, 8 plus 3, so 8 characters for the name plus 3 for the suffix, and that is called the DOS naming scheme. And this is why we have the 11 characters here. But yeah, nowadays you might want to have longer file names, and this is also possible in FAT. It's called file name hermaphroditic function, and we will have a look at that later. Yeah. Yeah, so a problem with that file name reconstruction obviously is when you don't have the first character, you can also have several files that have the reconstructed file name IL, but as we don't know the first character, the first file could have been file, and the second one could, for example, be whatever, bile. And when the first character is deleted, we have two file names, two reconstructed file names that appear to be the same, but we don't actually know. Okay. Let's talk about the attributes very quickly that are integrated in the directory entry. We have a couple of essential attributes, like, for example, the directory entry, directory attribute, which tells you if an object is a file or a directory. We have an attribute that tells you if we have a long file name. So an additional file name, additional to that short DOS scheme name. And we can also have an attribute that tells us something about the drive name, which should only exist once in the file system. So if you find if you find several drive names in the file system, then that could be a hint for like some kind of inconsistencies. Yeah, and if none of these attributes are set, then the entry belongs to a regular file. Yeah, there are also additional attributes that can be set, like read-only, hidden, system, or archive, but they are non-essential. And therefore, as you by now know, you should be careful with these attributes, but they are essential and important. Okay, there are a couple of attribute. So there can be certain configurations that are known as unusual, like attribute configurations. For example, if you have the combination of label plus system plus hidden plus read only, then that can be considered unusual, and you should definitely check it out, what is happening there. Okay. I also already told you that there are a couple of timestamps. We, for example, we usually have 3 timestamps. We have the created, last accessed, and last written timestamps, and they are called MAC times, so modified, accessed, created. And this is how you can try to memorize these timestamps. All these timestamps are in relation to the local clock, so you should definitely check out the local clock of a system in order to find out if the timestamps are trustworthy and if there are any inconsistencies. You also should be aware that there are different granularities. For example, the created timestamp has an optional time specification. It's usually for FAT file systems. This is also indicated here. Yeah, here. It has a different granularity than the other timestamps. So this one has the granularity tenths of a second, but the other ones have a different granularity. So last access has exact granularity to a day, and the last written has the exact granularity to 2 seconds. So you should be aware of the fact that not all timestamps work the same. And there's also no precise specification as to which operations set these timestamps. There are a couple of papers, scientific papers, that examine when certain timestamps are set and when not. But for example, if you would investigate a certain case where a certain timestamp is very important, you should try to check out when this timestamp is set or changed and when not, to avoid confusion or especially to avoid drawing wrong conclusions. And this also depends on the operating system, for example. Okay, Okay, I have the slide like 2 times on there. Yeah, this slide basically tells you exact the same thing as this slide. Yeah, I think I will change it after the lecture so that you only have one slide and are not confused by that. Okay, next category, file name data. What does the file name data category tells us? Should be pretty easy to answer. Anyone? Exactly, the file name. Yeah, I already told you that for FAT, the metadata and file name data category are mixed up. So you have the file name already in the metadata. But yeah, there are still a couple of things that we that we need to discuss for that category. So, for example, we have some allocation status and linking that we need to discuss. And for example, if a directory entry, so not a file allocation table entry, but a directory entry in the root directory is unassigned, the first byte contains like a special value. And I already told you that the first letter of a name is lost when the file is deleted, and that also holds for directories. So yeah, so the directory entry contains a pointer to the first cluster of the file. We already knew that. And the file allocation table structure contains references to the following clusters. It also contains entries or let me start again. When the file allocation table entry is not 0, then it points to the next cluster. If it is 0, then the cluster doesn't belong to a file or directory. And we also already know about the end of file and damaged marker, but let's check out an example again for the file allocation table and the root directory. So here you can see an example entry in the root directory for file 1.dat. We have the starting cluster of 40 and a certain size. And by knowing where to start, we can have a look at the file allocation table and check out cluster entry 40. Then we'll see here that there is a 41 in that entry. So 41 also belongs to file 1.dat. We go to that entry, check out the contents. See here, cluster 45 also belongs to this file. We go over to that cluster entry and see here that we have an end of file marker, and that's it. Yeah, that's it. So now we know how many clusters and which clusters belong to file 1.dat and how much memory is allocated to the file, and with the size we also know how big the file really is, and all of this will be interesting later on. But let's talk about the maximum size of the file allocation table first. So the maximum size of the file system is based on the maximum size of the file allocation table entries, and this is the numbers we already talked about. So for example, FAT32 uses 28 bits for addressing clusters, and therefore you can only address a maximum number of a theoretical maximum number of clusters with that kind of addressing scheme. And in this table, you can see how many clusters you can address with the different file system types. And you can see here that with FAT32, you could address a maximum, or you could use FAT32 for drives with a maximum of, more or less 2 terabytes. So this is the maximum drive size that FAT32 can handle because of the maximum number of addressable clusters according to the maximum file allocation table entry size. Okay, I hope that's clear. Yeah, and on large disks, the clusters must contain many sectors. So in order to maximize these numbers, the cluster size must be as big as possible. And therefore, you also create lots of slack space. And you can also create lots of fragmentation because of that. Okay, there's a question in the chat. What is the difference between theoretical and practical numbers of addressable clusters? So I know it was a little bit confusing, but in the beginning, I told you that the data area starts with cluster 2, and all the reserved and the FAT allocation data area does not belong to the addressable numbers of clusters. So in theory, you could have more addressable clusters if you would use the reserved area and the FAT area and stuff. But in practice, you cannot use the reserved and the FAT area. So that's the difference between theoretical and practical addressable numbers of clusters. So the whole file system is bigger than the actual usable file system part. Okay. But did you get that? Like in order to maximize the handleable size for FAT32, for example, you would need to make the clusters as big as possible. So have as many sectors grouped into one cluster as possible. And this maximizes the handleable space, but it also maximizes the possibility to have slack space and fragmentation. Okay, so in order to determine between the different FAT types, we could, of course, check out the boot sector and see what kind of label is in there. But as this not necessarily needs to be correct, you should be also possible to determine the FAT type by calculating certain numbers or have a look at certain numbers. And you can determine the FAT type by counting the numbers of clusters in the file system. So for FAT12, for example, you should have less than this number of clusters. For FAT16, you should have less than that numbers of clusters, but more than FAT12. And for FAT32, you should have more than this number of clusters, so more than FAT16. And by that, you can be very certain to get the correct FAT file system type. Okay, but let's talk about directories again. So what you need to know about directories is that obviously the directory attribute needs to be set in the directory entry of a directory. And if a new directory is created, a new cluster is occupied and it's zeroed out. That is very important. And the size field in the directory is meaningless and should always be 0. So if that's not the case, then there's something going on. Yeah, because the directory itself has no content and therefore has no size. And the actual size of the directory, including all the contents in there, can be calculated by traversing the cluster chain. Okay. And you always have two entries in the directory. You have the point and or dot and dot dot for the current directory and the parent directory. You should also know that the timestamps of these directory entries do not change. And yeah, so it can be confusing as the directory entry and the parent directory can be changed. Yeah, so there could be it could come to a situation where you have contradicting timestamps, yeah, but for directories, yeah, you should be aware that this is like this is normal in some way, yeah. Okay, and in order to restore directory names, we have to do the following or imagine that situation. We have a directory entry for a directory called dir1, and the directory entry tells us that the directory starts in cluster 46. So in cluster 46, you have the current directory. Here you have the parent directory, and you have a file that belongs to or is somewhere in the directory hierarchy, but has this entry for cluster 48 for its own contents. And if a directory is deleted, then as with the files, only the first letter of the directory entry name is set to this specific value. And I think I need to reorder the slides a little bit because that's what I was telling you at the first slide of the file name data category. So as with regular files, if a directory entry is deleted, the first byte is set to this specific value, which means that the directory is deleted now. Yeah. But the thing is, you can still access or you still have the information about the cluster where the directory belongs to or which is referenced in the directory entry. So you can still access the contents of the directory. And let's now imagine that situation. What if a directory entry is reused? So we had directory number 1, which started at cluster 46. We deleted the directory entry by deleting the first byte, so the D, and put a special character in there or special byte in there. And after that, the directory entry was reused for directory number 2, which then also used cluster 46. And we now have, so the clusters of the original directory are then no longer as easy to find as it was before, because it was reused by directory 2. However, you can still systematically search every unused cluster for the dot and the dot dot entry, so for the current and the parent directory. And this way you can still find deleted directories. You can also find them in Slack space by using the current and the parent directory and searching for the entries for the deleted directory. So it's difficult, but it's possible. Okay, what else does belong to the file name data category? Drive names also belong to that category. And I already told you that directory names can contain drive names, but usually you only have one in the file system. And it's usually in the root directory, but can also be anywhere else. And yeah, and you could, for example, place drive names in subdirectories and hide data in there. That's why you need to check that out. And something else we need to talk about is the file names. We already saw that there are two types of file names. We have the regular file name with the 8.3 naming convention, so 8-character file name, 3-character suffix. And I already told you that it's also possible to have long file names in the FAT file system. And in order to do so, you need to use a special directory entry. It's called long file name. And there you can put 13 Unicode characters in. Yeah, and even if an entry has more than 13 characters, the LFN, the long file name entry, can be extended by creating several new long file name entries. So each long file name entry has a short file name directory entry. And this is necessary to handle the fact that long file name entries cannot contain times, sizes, and so on. You will see it in a minute. So this is the structure of a long file name directory entry. So we have in the first byte we have a sequence number, and again the allocation status. Then we have the first 10 characters, or the first 5 Unicode characters of the file name. We have a file attribute. We have some kind of reserved area checksums. Then we have again 5 Unicode characters of the file name. And here we have another 2 characters of the file name. And this is the structure of the long file name directory entry. And how does it work exactly? Okay, so we have the long file name entry always before the short file name entry to which the long file name entry belongs. So let's check that out. So we have the short file name entry here with the short name my long, and you see that sign. I don't know how it's called in English. In German, it's a tilde, and then a one, and the suffix. And this actually tells you that there must be a long file name entry somewhere. As I said, usually after that short file name entry. And after the short file name entry, you have the first part of the long file name entry, so my long file. And this is the first part. And the second part is name.rtf, so the rest of the long file name and the suffix. And yeah, this is how the long file name structure works and is extended in case the file name even exceeds the first long file name entry. You can have another one and another one and another one. Yeah. Yeah, and as you can see here, the long file name entry has a sequence number in the first byte, which counts how many of these entries you have. And at the end of the chain, the sequence number is an XOR with 0x40. And yeah, it basically tells you that the long file name entry chain ends here. Yeah, so yeah, here you can see that in the hex editor out excerpt, you can also see here that the short name that you have the last part of the long name in the first row, and then backwards the remaining parts of the file name. Okay, I think that's clear. Oh, okay, I'm already running out of time. But we only have 5 slides left. So in terms of file name data analysis, what you should do is you should run through all the file names, find the root directory, and yeah, you should check out the directory hierarchy, and yeah, you should also check out all the long file name entries, and you should be aware of the fact that they are stored in fragments. So yeah, just to be aware that the long file name entry does not store the file name in only one entry, but in several entries and several fragments. And if you want to reconstruct a deleted file or deleted directory, you should check out the first byte of the name. A directory entry consists of zeros, indicates the end of a directory entry. And you could also hide data behind that entry. Yeah, and you should do a logical search on all sectors to also find this data, this hidden data. Yeah, I think we shouldn't talk about defragmentation for now. Let's check out the summary very quickly. So what happens when you create a file in the FAT file system? So let's say we create a directory 1 in the root directory and file 1.dat. Then what happens is, or what you should check out is during an analysis is read the boot sector and identify the position of the file allocation table, the data area, and the root directory. Then you could search for dir1 in the root directory. Let's say it's in cluster 90. Then you can find that by by checking out the cluster that is referenced in this entry here. Then you should read out the content of cluster 90 and search for unallocated directory entries. Then you should be able to find the directory entry with file number 1.dat, which contains a reference to the cluster. The data content is in there. In this case, it's cluster 200. So you should check out this cluster in order to get the file contents. And for the deletion process, what is done is the first character of the file is set to 0xE5, so the special byte that indicates the allocation status of the file. Then the file allocation entries are set to 0 in case the file is deleted. But as the first block and the file size is still there, you can still reconstruct that file. And I also already told you that you can also reconstruct directories in cases they are lost. So that's the very quick summary. To conclude, the file allocation table file system has a well-documented and simple data structure. As I said, if you want to learn more about that, or if I was too fast or said something confusing, you can also check out the book from Brian Carrier, where he explained all of the details very well. The modification of access times is unfortunately not well documented. So in order to get more information about that, scientific papers need to be examined. And the allocation strategies for unallocated blocks are dependent on the operating system and the file system driver, but usually you can work with the assumption that clusters are allocated linearly, and this is actually also what the sleuthkit, for example, does. So thank you for the attention. Sorry for needing more time than I think I'm 5 minutes late, so I'm sorry for that. I hope everything was clear. If not, as I said, ask me in the forum or check out the book from Brian Carrier. And we'll see each other next week then for NTFS. Thank you very much.